Okay, we are at section 8.2. Uh, yes, isolated system analysis model of energy on isolated systems. Let's go to the PowerPoint. So we've seen this before. We have a book at rest, held at rest, and then released. So as a lower at the lower position, the book is moving and has kinetic energy K, and it's lost potential energy. So let's look. So delta K, the change in kinetic energy, plus the change in potential energy equals zero, which whatever kinetic energy is gained is transferred from the potential energy. So um, in this particular case, the equation above is gravitational potential energy, but it's really any kind of potential energy. Um, it could be spring potential energy. The change in kinetic energy plus the change in potential energy is equal to zero. So the transformation mechanism is work done on the book within the system by the gravitational force. Um, so whenever the energy of mechanical energy is equal to the kinetic energy plus the potential energy. So the sum of the mechanical energy or the change in the mechanical energy is equal to zero. So the kinetic energy final minus kinetic energy initial plus the potential energy final minus the uh, potential energy initial is equal to zero. Well, let's get the positives, the KF and the UF, and if we subtract the KI and UI, they become positive. So kinetic energy final plus potential energy final is equal to the initial kinetic energy plus the initial potential energy. So we have 1/2 final velocity squared plus mg y position final equals 1/2 um, mass times initial velocity squared plus mg times the initial y position. So E of the energy of the mechanical energy plus the internal energy equals to the total energy initial equals the total energy final. So the change in energy of the system is equal to zero. Let's see, a rock of mass m is dropped to the ground from a height h. A second rock with mass 2m is dropped from the same height. When the second rock strikes the ground, what is its kinetic energy? Is it twice that of the first rock, 4 times that of the first rock, the same as that of the first rock, or half as much as that of the first rock, or it's impossible to determine? Well, we know from the height that it's um, mgy. So the second rock will be 2 mgy. Well, that's going to be transferred to kinetic energy, but it's only twice the mass. So it's going to be uh, twice the kinetic energy of the first rock because it's twice the potential energy. There's the answer, twice that of the first rock. Okay, 3 identical balls are thrown from the top of a building, all with the same initial speed as shown in the figure. The first is thrown horizontally, the second at some angle above the horizontal, and the third at some angle below the horizontal. Neglecting air resistance, rank the speeds of the balls at the instant each hits the ground. Um, well, we're going to find out that it's, let's see if I'm in the uh, right place. No, I'm not. We're going to find out that they're all equal. Um, let's get to where I have to read. Now, the first and the third ball, they speed up after they are thrown, whereas the second ball initially slows down because it's got an initial vertical velocity. It slows down, but then it speeds up after reaching its peak. The path of all 3 balls is a parabola, and the balls take different times. Now, they're not all going to land at the same time. They land at different times on the ground. Uh, but they all have different initial velocities. All three balls have the same speed at the moment they hit the ground because all start with the same kinetic energy, and because the ball Earth system undergoes the same change in gravitational potential energy in all cases. So delta UG is the same in all cases because they're all starting from where that gentleman is launching them from his hand. Okay, so notice that in an isolated system, if you recall the previous graph, we had all these arrows going in and out, all the transfer mechanisms, heat, mechanical wave, electrical transmission, all of those. Well, everything in an isolated system, everything stays within the system boundary. So the total amount of energy in the system is constant. Energy transforms among the three possible types: internal energy, potential energy, and kinetic energy. All right, and internal energy could be something like heat, like we talked about the block and the surface. Well, if that's the system, the internal energy of the surface and the internal energy of the block are going to increase, but they're internal to the system. We define it as the block surface system, and so the change in the mechanical energy of the system is equal to 0. It's all stays within the system boundary. If no non-conservative forces act, then the change in mechanical energy is equal to 0. And with that, we'll stop and we'll go on with the next section in the next video: situations involving kinetic friction.